Hello, my name is Emmanuel Lellouch. I work at Paris Observatory in France. And the topic of my lecture will be about the tenuous atmospheres of the solar system. So the idea of this lecture is to give you a brief overview of these tenuous atmospheres, reviewing a few relevant physical concepts, and focusing on the three densest and also best characterized of tenuous atmospheres, namely those of Pluto, Triton, and Io. So when we think about solar system atmospheres, we typically think of two broad classes, the giant planets and the telluric planets. So for the giant planets, both the gas giants, Jupiter and Saturn, and the icy giants, Uranus and Neptune, we have atmospheres that are dominated by hydrogen and helium, and in which the other elements are mostly in chemically reducing form. So for example, carbon is in the form mostly of methane, oxygen is mostly in the form of water vapor, and so on. These atmospheres are primitive in the sense that they were captured at the time of formation of these planets, and they have undergone little evolution. This is because escape is negligible on these massive bodies, and also because these atmospheres do not directly interact with the solid surface. So for example, although there is photolytic conversion of methane into higher order hydrocarbons, those are being transported into the deep atmospheres, and there they are recycled back to methane. On the other hand, the atmosphere of the telluric planets are dominated by heavy compounds such as molecular nitrogen, oxygen, or carbon dioxide. These atmospheres are secondary, having been produced by outgassing and volcanic sources, and they are strongly evolved due to strong interaction with the planetary surfaces. This includes chemical equilibria with rocks, geochemical cycles, volcanism. And these atmospheres have been subject to long-term evolution, including a variety of processes like runaway greenhouse, escape, or impacts by comets or asteroids. And the same is probably true for Titan's thick nitrogen atmosphere, which also falls in this category of secondary atmospheres. However, in addition to these two broad classes, there are actually no less than 12 other planetary class objects that hold some atmosphere or an atmosphere of some kind. And these bodies are, by increasing distance from the sun, Mercury, the Moon, Ceres, the 4 Galilean satellites, Io, Europa, Ganymede, and Callisto, 3 of Saturn's moon, Enceladus, Dione, and Rhea, and then Neptune's moon, Triton, and Pluto. So all of these objects are relatively small by planetary standards. Therefore, any atmosphere around them will be relatively weakly bound gravitationally, and therefore subject to escape. And therefore, the fact that these atmospheres exist implies that there are some supply mechanisms that we will review. But first of all, what really defines a thin atmosphere? Where is the limit between a thin and a thick atmosphere? Here there are several possible criteria. The first and most important distinction to make is whether atmospheres are collisional or not collisional. So in an atmosphere, the collisional limit is reached when the gas mean free path against collisions becomes comparable to the atmospheric scale height. This is the classical definition of an exobase. And an exobase corresponds to a typical column density of 3 times 10 to the 14 molecules per square centimeter, or if expressed in pressure, to a typical pressure of a few picobars. Above the collisional limit, we can speak truly of atmospheres. And clearly, this is the case of Pluto and Triton, which have about 10 microbar atmospheres, and Io, at least on its day side, where the pressure is several nanobar. Below the collisional limit, which means actually that the exobase is at the surface, the atmospheres are better called exospheres. And clearly, this is the case of the Moon, Mercury, and Ceres. Interestingly, most of the 12 bodies are in fact near the exospheric limit, being probably collisional in some parts of the body and restricted to exospheres in other parts. And for bodies that are close or within the exospheric regime, an important aspect is that a fluid description becomes invalid, as essentially it breaks down when the mean free path becomes comparable to horizontal scales. And in this case, particle description of the flows as opposed to fluid descriptions are needed. So this is the first criterion, collisional limit. But there are another criterion to distinguish between thin and thick atmosphere is whether the atmosphere is transparent or opaque to different sources of energy. For sputtering is a process of bombardment of a surface or an atmosphere by energetic particles. So for sputtering, the typical penetration depth is of the order of 10 to the 15 molecules per square centimeter in an atmosphere. So the pressure limit for an atmosphere to be thick against this process is about 1/100th of a nanobar. For solar radiation, the pressure below which an atmosphere is transparent at all wavelengths, of course, this is strongly dependent on the atmospheric composition, but typically this corresponds to about 1/10th of a nanobar. And finally, we will discuss later sublimation-driven atmospheres, and here the distinction between thin and thick, as you will see, is related to the importance or not of latent heat exchanges on the heat budget of the surface, and as we will see, the limit is at about 0.1 microbar. So we have here a series of criteria, and of course, against any of these criteria, Mars atmosphere, whose pressure is about 7 millibar, is robustly a thick atmosphere. Here is a brief overview of all these tenuous atmospheres of the solar system. So I'm showing this table only for reference. I'm not going to go through in details, but it gives you a basic overview of the properties of these 12 known tenuous atmospheres. So in terms of main composition, atmospheric density, which is expressed here either in pressure or density or column density, depending actually on how it was measured. And this table also gives you an idea of the origin of the atmosphere, and then some reference in which you may look if you are interested on further details of one or the other of these atmospheres. So what are overall the possible sources for tenuous atmospheres? First, we have to consider the case of objects covered by ice. In this case, a very important source, of course, is the sublimation of surface ices. And this process tends to maintain an atmospheric pressure that's going to be equal to the saturated vapor pressure of the ice at the relevant surface temperature. So what happens is that in regions where the pressure is less than the vapor pressure value, there is a sublimation flux that depends on the difference between the current pressure, the saturated pressure and the current pressure, and then divided by some thermal velocity, see here. And conversely, in region where the pressure exceeds the vapor pressure, there is a condensation flux until the two pressures become equal. So this equalization of surface pressure to the saturated value is a fast process which happens on time scales of minutes only. Sublimation equilibria, of course, are extremely sensitive to temperature because the vapor pressure laws are exponentially dependent on temperature. And as we will see later in more details, these vapor pressure equilibria can be either global on a planet or local. And the sublimation condensation exchanges may affect or may not affect the surface energy budget. A second source of atmosphere is direct outgassing, which may be volcanic outgassing or cryovolcanic outgassing. The distinction between volcanism and cryovolcanism is that in volcanism, the erupting material are actually molten rocks like lavas, while cryovolcanism is a process in which the erupting material is water. So in this mechanism, a volcanic source leads to the production of a local atmosphere with a pressure that is, of course, proportional to the source, but also depends on a sticking coefficient which represents the extent to which the ejected molecules will stick on the surface or bounce over the surface when they hit the surface. The third source of tenuous atmosphere is sputtering. So sputtering is the production of an atmosphere by impacts on the surface of different kinds of energetic particles. So these energetic particles can be the solar wind, can be micrometeorites, and especially important in the case of the moons of the giant planets, it can be charged particles from the planetary magnetospheres. So this process produces a rarefied, weakly bound extended atmosphere, which is called corona. But the process, importantly, is a self-limited one, because as we saw, exospheres become relatively quickly opaque to sputtering. So if you have a large gas production by sputtering, it will further inhibit the penetration of additional energetic particles. So this is for sputtering on a surface, but sputtering may also occur on a pre-existing atmosphere. And in this case, sputtering represents an additional source of heating, which may in particular enhance escape rates from the atmosphere. So we have three broad mechanisms, but it must be noted that in general, these different mechanisms may coexist, and actually, usually they do coexist. So we'll see later the case of Io, where we have coexistence of volcanic atmospheres and sublimation atmospheres. An interesting case of the coexistence of sublimation and sputtered atmosphere is represented by Jupiter's moon Ganymede. On Ganymede, we have a water ice surface that's being sputtered by the flow of plasma. And the flow of plasma consists mostly of sulfur and oxygen ions and electrons that corrotate with Jupiter's magnetosphere. So this corrotating plasma impacts the surface and causes the breaking and the ejection of surface species like water itself or OH or atomic oxygen, atomic hydrogen. But it can also produce it can also lead to the chemical production of other species like O2 and H2, which this is a process called radiolysis. So an interesting thing is that Ganymede has an intrinsic magnetic field. Therefore, it has a small magnetosphere that is embedded within Jupiter's magnetosphere. And therefore, most of the plasma impact and sputtering will occur at mid to high latitudes where the magnetic field lines are open. This is visible, for example, on this image, which shows emission from atomic oxygen with a auroral-like structure. Well, in addition to sputtering, we may have a source, there may be a source of water vapor from sublimation of the ice on the day side, mostly actually at low to mid latitudes where the temperature are the highest. So these processes are still very poorly characterized by observation, but the combination of the two processes is expected to lead to a complex distribution for the various atmospheric species that are being produced. And this is due to a combination of factors like the complex distribution of the incident plasma, the variability of the ice composition, especially in terms of the H2O content, the variability of the surface temperature that affects both the sublimation and the sputtering efficiency, and also the lifetime of the produced atmospheric species versus chemical loss and within the atmosphere and reaction at the surface. So we have models for the atmosphere of Ganymede, and for example, here I'm showing here on the left model predictions for Ganymede exosphere in the case where only sputtering is considered, so in the case where we have negligible sublimation component. In this case, water is confined to a sputtering component at high latitudes, as I said, because the plasma impacts the surface mostly there. In contrast, molecular oxygen and molecular hydrogen that do not condense nor stick to the surface can diffuse from their production region to the rest of the object, and therefore they will have a much more extended distribution. If, however, we now consider, in addition, a sublimation component, then in this case, the picture changes considerably, at least for water, because now we have a collisionally thick atmosphere of column density of about 10 to the 16. And also this sublimation component is denser and more extended on the trailing side compared to the leading, in fact, simply because the trailing side has lower albedos and therefore higher temperatures, therefore a higher sublimation component. But these are simply models, and all of this so far is very poorly characterized by observation. But note that we expect a lot of progress from the operation of the JUICE mission. This mission, which in starting about 2032, will have an orbital phase of Ganymede, and therefore which should be able to map the different species of this atmosphere. Okay, before moving to the denser atmosphere of Pluto, Triton, and Io, let me say a few words about cryovolcanic plume-like atmospheres, which have attracted considerable attention because they have possible astrobiological implications. So we have one clear case for a plume atmosphere, which is Enceladus, and one more tentative case, which is Europa. So Enceladus, one of the really most spectacular results of the Cassini mission was the discovery of multiple active plumes on Enceladus. And these plumes are localized in the South Polar region, and they are concentrated along 4 fractures or fissures called informally the tiger stripes. And these fractures are the place of internal activity due to tidal interaction. And in this place, the surface temperature appears to be dramatically enhanced. These plumes eject about 300 kilograms per second of gases and micron-sized icy grains. And they form a predominantly water plume atmosphere with column density that have been measured actually by Cassini from the UV instrument to be about 10 to the 16 molecule per square centimeter. Now, in terms of the gas composition, the composition of the plumes has been revealed by the Cassini ion neutral mass spectrometer. And initially, these data seemed to show the detection of many species beyond water. But in fact, it appeared that some of these peaks here, especially those at heavy masses, were due to the formation of these species within the instrument itself. Nonetheless, it seems that in addition to water, we have the secure detection of at least 4 molecules: CO2, methane, ammonia, and molecular hydrogen. In addition, on Cassini, there was a cosmic dust analyzer instrument which analyzed the icy grains from the plume, and they found them to have also a very interesting and rich composition. Some grains appear to be essentially pure water, but other grains include salts, like, for example, sodium chloride, and other grains contain also high mass organic ions. So this is interesting from an exobiological point of view, because the composition, both of the gas and of the solid of the plumes, must somehow trace the composition of the ocean that is known to exist below the icy crust of Enceladus. And okay, I will not discuss this too much, as this is largely beyond my competence, but it appears that the plume composition may be evidence that the ocean directly interacts with the rocky core inside Enceladus with possible processes like hydrothermal vents. So beyond these very interesting implications, it appears that in fact the plume atmosphere of Enceladus has a very large influence on the entire Saturn system. So the icy grains from the plume are at the source of the E-ring that is being seen here. And also they coat Saturn's satellite with bright material that is responsible for their high albedo. And the gas that escapes Enceladus forms a neutral torus, which is dominated by water gas. And in favorable geometries, the torus can be observed in absorption against Saturn. So here is an observation of Saturn by Herschel, which shows an absorption due to water vapor from the Enceladus torus. And from this observation, it was possible to measure the torus density, and it was inferred from this observation that actually the Enceladus cryovolcanic activity may be even the ultimate source of water vapor in the upper atmosphere of Saturn. Europa also, in all likelihood, has a surface ocean, and therefore plume atmospheres have also been searched for on Europa. But this time, in fact, the results are ambiguous. There have been 3 different and independent techniques that have reported the existence of plumes. One is the use of UV line imaging with the search of oxygen, neutral, and Lyman alpha hydrogen emission. The other technique is the search for plume opacity as in transit against Jupiter, when Europa transits Jupiter. And the third method is a direct search for water fluorescent emission from the plumes. Most of these observations actually have given negative or marginal results, as you see. And this is rather marginal. And this is one detection in 17 observations, and even then is relatively marginal. But so most of the results are negative, and even the results that are claimed to be positive, well, they result in column densities of water that are not very consistent between observations. Of course, the plumes can be variable by nature, but another worrisome aspect is that, unlike what happens on Enceladus and of course on Io, the problem is that endogenic hotspots have never been observed on Europa. So there is a problem of the mechanism for plume generation. And so all in all, I think the evidence for the Europa plumes is marginal. Okay, so now for the rest of the talk, I will focus on the three densest of the tenuous atmosphere of the solar system, namely those of Pluto, Triton, and Io. This atmosphere is sublimation driven in the sense that the surface ices are entirely or predominantly the immediate source of the atmosphere. So the ices, these volatile ices are N2, methane, and CO on Pluto and Triton, and SO2 at sulfur dioxide at Io. For Pluto and Triton, because N2 is much more volatile than methane, and because CO has a small abundance in the ice relative to N2, because of that, the atmospheres of Pluto and Triton are in fact dominated by molecular nitrogen. So as we have seen, such atmospheres are in vapor pressure equilibrium with the surface, but an important question is whether this equilibrium is local or global. And what is the role of the atmosphere on the energy budget of the surface? So if you consider a planet covered by frost, the ice temperature and its time evolution is defined by the balance between insolation, thermal radiation from the surface, thermal conduction, and latent heat exchanges. Here, L is the sublimation latent heat, and m dot is the mass sublimation flux. And as this is shown here in the example of Pluto, there is a global transport of volatiles and energy from the surface, from the summer hemisphere to the winter hemisphere, or also from the day side to the night side. So this is the essential idea of volatile transport models. And of course, an important question is whether the latent heat exchanges affect or not appreciably the temperature budget of the surface. And this is primarily determined by the comparison of the latent heat term to the radiative term. So if the latent heat term is negligible with respect to the thermal flux from the surface, then each frost has its own energy budget and its own temperature. In contrast, if the latent heat term dominates over the radiative term, then all frost will be at the same temperature, which means that the atmospheric pressure will be horizontally constant. So we can define a kind of isothermality factor that represents the ratio here of the latent heat term to the radiative term. So if we put numbers on this, we find that on Pluto and Triton for N2, the latent heat exchanges vastly dominate the energy budget, which means that the atmospheric pressure at a given point in time is constant. On Io, in contrast, where the pressure is only about 1 nanobar, this isothermality factor turns out to be much less than 1, meaning that the latent heat exchanges are almost negligible. So each SO2 frost maintains its own temperature and therefore its own local pressure. Another way to see this is to ask the question, is the atmosphere able to redistribute heat from the solid hemisphere to the night side by means of latent heat transport? And to estimate what would be the required speed of such a sublimation wind. So for that, we can write that half of the solar energy deposited in the summer hemisphere, half of this energy is transported to the winter hemisphere. So we can find the required mass flux. And by assuming some vertical thickness of the flow, we can deduce the required speed. So if we put numbers, this approach requires only modest winds for Pluto and Triton of 1 meter per second or less, which is comfortably less than the speed of sound. On Io, in contrast, due to the fact that the atmosphere is much thinner, the redistribution of heat by the winds would imply strongly supersonic winds, which of course is not a realistic case for maintaining a constant surface pressure. So clearly we have two different regimes. On Pluto and Io, we have isothermal frosts and constant surface pressure, except of course for topography, at a given point in time. So in this respect, we can call this atmosphere thick. But of course, this leaves the possibility that the pressure will vary along the orbit in relation to the seasonal variation of the insolation. On Io, the atmosphere is thin from this point of view. Individual frosts have their own temperature and control locally their local atmosphere, and there are large horizontal variation of pressure. So let's focus now more on Pluto and Triton. On both objects, but especially on Pluto, we now have evidence that the pressure varies with time. And this is evidenced by stellar occultation measurements that have revealed that Pluto's atmosphere at some reference level has typically quadrupled in the, since the discovery of Io's atmosphere in 1988. And there are hints that the pressure may have started now to reach a plateau in recent years. And there are also hints for pressure evolution on Triton, but those are so far less documented, although a very good occultation data set has been observed a few years ago, and it's still under analysis, but it will tell us more about the pressure evolution on Triton. Now, even before the New Horizons probe explored Pluto in 2015, volatile transport models have been applied and developed to try to understand this pressure evolution on Pluto. So these models have to make assumptions. And the main assumptions are, where are the volatiles, or where are the reservoir of volatile ices? How big are these reservoirs? And what are the other thermal parameters that will control the surface, like thermal inertia in particular? And here you have example of old pre-New Horizons volatile transport model. And without going into the details, you can see that these models have come with rather different prediction on the overall pressure evolution with time. This kind of model has also been developed for Triton with the same questions and unknown in their parameters. And although Voyager 2 flew by Triton in 1981, it could not answer this question. And in particular, because Voyager did not carry a near-infrared instrument that could have mapped the distribution of ices. So we don't know for sure where the volatile ices are on Pluto, are on Triton, and therefore this is a big limitation for the volatile transport model of Triton. But for Pluto, we now have the answer. The big discovery of New Horizons was that there is a depression with a depth of several kilometers. It's called Sputnik Planitia. It is filled of nitrogen ice. And this depression holds a nitrogen mass equivalent to a reservoir of hundreds of meters of ice. And in fact, although it was initially surprising to find this depression at low latitudes, in fact, it was quickly understood that this is an expected outcome of atmosphere surface exchanges on the long term. Because essentially, given the orbital parameters of Pluto, it turns out that on an annual average, it is the low latitudes that experience a minimum of insolation. Therefore, this is where nitrogen ice will tend to accumulate. But in addition, very important is that we have a depression. And therefore, in the depression, we have a higher pressure. So if we have a higher pressure, we have a higher condensation temperature, and therefore a higher infrared cooling rate, and therefore a higher condensation rate. So a depression at low latitudes is where we expect the nitrogen ice will migrate and accumulate. And indeed, there have been simulations starting with a uniform distribution of all volatile ices, and this simulation quickly converged to the trapping of all of the N2 ice into the basin. And now these models with appropriate N2 ice reservoir, they are being used to explain the recent pressure variation. And in fact, they are able to reproduce the pressure variation and to make predictions on what the fate of Pluto's atmosphere is going to be in the next years. And so the current models predict that Pluto's surface should reach a plateau fairly soon and then decrease. And the decrease of pressure will occur soon because, in fact, the subsolar latitude is now going to high northern latitudes, so that the insolation on the nitrogen reservoir is starting to decrease. But note that although Pluto is receding to the sun and will be at almost 50 AU from the sun at its maximum distance, there will never be, according to this model, a true collapse of Pluto's atmosphere. Another effect of the condensation sublimation cycle is visible in the near surface thermal structure of Pluto's atmosphere. So in the lower atmosphere, there is the temperature shows a very large positive temperature gradient for reasons I'll explain later. But here we are interested really in the first few kilometers. And the New Horizons observation returned two temperature profiles from radio occultation, especially one of them, which is marked ingress here, was obtained above the N2 ice region, and the corresponding profile goes to very cold temperatures before changing a sign of the temperature gradient in the first kilometer. And this is now being understood as the effect of the diurnal sublimation condensation cycles. In fact, what happened is that during the day, the sublimation of the N2 ice injects a layer of cold N2 gas, which creates a boundary layer close to saturation. In fact, it's interesting that sublimation condensation exchanges seem to control entirely the dynamics of Pluto's atmosphere. On Triton, we do not have detailed temperature profile in the lower atmosphere, but there is also indirect evidence for a convective boundary layer in the first 8 kilometers. So as we saw, in addition to N2, there is methane and CO2 and CO ice on the surface, and those must also control the abundances of these gases in the atmosphere. So to some extent, this is similar to the case of Mars, where in addition to CO2 ice, the surface holds water ice. But there is a complication in Pluto and Triton, namely that methane and CO are miscible in N2. And on Pluto, there are in fact regions which are dominated by methane ice, and other where methane is only diluted in nitrogen ice. So this is a complex situation, and people have wondered how to calculate the atmospheric abundance in this kind of situation. But there is a fact nonetheless, which is that the methane abundance in Pluto's lower atmosphere is about 20 times larger than on Triton. And general circulation models that incorporate these different volatiles now find that the elevated methane abundance in Pluto's atmosphere is ultimately caused by the existence of these regions that are being shown here in green and which are rich in methane ice. So once the ice atmosphere equilibria are established, we have a predominantly N2 methane major contribution, and then this major contribution will drive a photochemistry that's actually similar to Titan. And therefore, ultimately, the difference in the methane abundance in Pluto and Triton, this factor of 20, will have large consequences on the detailed composition of these atmospheres and also on their thermal structures. New Horizons has revealed the chemistry of Pluto's atmosphere. It has detected vertical profiles of several hydrocarbons. There is one remarkable aspect here, which is that the mixing ratio of methane increases quickly with altitude. So to some extent, to some extent, this may be expected as being the effect of diffusive separation, because methane is lighter than N2. But in fact, the increase starts very close to the surface, which implies that vertical mixing is poorly efficient. And this is probably related to a highly stratified lower atmosphere. N2 and methane are then at the origin of a Titan-like chemistry, with far UV photolysis converting methane irreversibly into hydrocarbons, and extreme UV photolysis of N2 and reaction with carbon products leading to the formation of nitriles. And actually one of them, HCN, has been detected not by New Horizons, but from the ground using ALMA. And the interaction with solar UV also leads to photoionization, producing ions that may be initiating the haze production. So we have a production zone for these molecules in the middle atmosphere, transport to the lower atmosphere, and condensation losses in the lower atmosphere. And this explains the positive slope of the hydrocarbons mixing ratio, which increase with altitude. This situation, in fact, is similar to Titan, where most of the hydrocarbons also increase with altitude. On Triton, we know much less, but an essential difference is that because the methane abundance is much weaker and the lower atmosphere temperatures are much colder than on Pluto, the methane is essentially restricted to the near surface only. So the methane gas is essentially optically thin to the solar UV throughout the atmosphere. So the methane photochemistry is restricted to the lower atmosphere, while in contrast, nitrogen is photolyzed higher in the atmosphere, typically around 300 kilometers. So essentially, we have here a decoupled chemistry of methane in the lower atmosphere and nitrogen in the upper atmosphere. So in this case, the production of nitriles is expected to be much reduced compared to Pluto. In fact, Triton's atmosphere composition remains poorly characterized, and the hydrocarbons that are expected from the photochemistry of methane are not detected yet. They are not detected, but there is a relatively direct proof of their existence, which is the evidence of photochemical haze in the lower atmosphere of Triton that you can see here on the limb. And so this photochemical haze is the end product of the photochemistry. On Pluto, we have also an haze, and actually a much more extensive haze that extends up to 600 kilometers. And this haze has very interesting structure on which I'm not going to discuss in detail, but essentially it has a fractal structure, and also it shows a layered structure that may be evidence for the role of waves, of atmospheric waves, probably excited by the diurnal sublimation cycle. So the formation of Pluto aerosols is thought to be similar to Titan, but there are probably some important differences. In Titan, it is now understood that the haze particles are initially formed by ion-neutral chemistry in the upper atmosphere, and that these first small haze particles can grow to much larger masses by becoming charged and attracting electrons and ions from the ionosphere of Titan. Below the ionosphere, aerosols further grow by other processes such as aggregation, sedimentation, and surface chemistry. And once they reach the stratosphere, they are being influenced by dynamical processes and also ultimately by the condensation of hydrocarbon and nitrile acids. On Pluto, most of these processes are thought to occur, but there are differences. In particular, the role of ionospheric chemistry is more difficult to establish simply because Pluto ionosphere has not been detected. And another major difference is that on Titan, the haze precursors are formed at very high altitudes, while the pure ices condense only in the lower atmosphere. In Pluto, because of the colder atmosphere, the hydrocarbon and nitriles can condense at high altitudes much closer to the haze formation region. And therefore, a large component of the haze may be produced by direct condensation. There is an interesting and unresolved question why does Pluto surface present large variation in appearance and albedo, given that the haze material is produced everywhere, and so the haze material should uniformly coat the surface? We can understand that sublimation condensation exchanges on diurnal timescales in the N2 ice region may quickly bury the haze particles. But for other regions of the surface, it's unclear why the direct chemical processing of the surface by solar photon is not masked by the permanent haze deposition. So let's now have a look at the thermal structure of Pluto and Triton into a little more detail. Here they are being compared to that of Titan and being placed on a common temperature pressure scale. So on Titan, we have a well-marked stratosphere due to the heating, absorption of solar visible and near-infrared light by atmospheric methane and haze. On Pluto, as I mentioned, there is a very large positive gradient, which is due to heating by methane. And remarkably enough, this was understood even before methane was measured in Pluto's atmosphere. On Triton, although the thermal structure is not known in detail yet, we know that the lower atmosphere is much colder than Pluto, and this can be understood as the effect of the much smaller methane abundance in Triton's atmosphere. So now let's look at the upper atmospheres. On Titan, above the maximum temperature, the temperatures are rather isothermal, and the upper atmosphere temperature, about 180 K, is due to first order to the balance between heating by solar UV and electrons or ions precipitating from Saturn magnetosphere, and cooling by HEN with possible contributions due to wave heating or cooling. On Triton, the upper atmosphere was measured to be about 100 K, and it is caused by the balance between energy deposition by solar heating and magnetospheric heating of N2 and by downward conduction. So in this sense, Triton's atmosphere is essentially a thermosphere, with the energy deposited above being transported by downward conduction. But because Pluto and Triton are both N2, it was thought that Pluto would exhibit a similar 100 K thermospheric temperature. And it was a very big surprise when new horizons revealed that Pluto's atmosphere is actually much colder, only about 70 degrees. So this implies that there is a cooling agent in Pluto's atmosphere, but so far it has not been identified, and the mystery is going on, as the identified species in Pluto's atmosphere do not appear to be sufficiently efficient coolers. So people have tried to find alternative explanation. One explanation has been that there is cooling by water vapor, but for this to be the solution, water must be extraordinarily abundant in the upper atmosphere. So this solution seems, in fact, a little far-fetched. There is a drastically different hypothesis that has been put forward, namely that the energy budget of Pluto's middle atmosphere is primarily not governed by hazes, but by the radiative properties of the haze. And it seems that for radiative properties of the haze that are assumed to be similar to those of Titan, both in the optical and in far infrared, Pluto haze seems to be able to radiate sufficient energy in the far infrared to explain the middle and upper atmosphere structure. So this is an interesting idea, but it needs to be validated. And remarkably, in fact, this prediction is testable by observation with James Webb, which will able to measure, if it exists, any large emission from the haze in the far infrared. Finally, the consequence of this low upper atmosphere temperature is that it makes Pluto's atmosphere more compact than was thought, and therefore escape rates are much smaller than previously thought. In fact, for both Pluto and Triton, the upper atmosphere are cold and the exobases are not very high, and therefore the thermal escape remains actually low. And when putting numbers on this, it appears that these escape rates, if they are extrapolated to the age of the solar system, they are relatively inconsequential for the object evolution. Yet there is a very interesting signature of Pluto's atmospheric escape on its moon Charon. Charon exhibits remarkably red poles, and the interpretation of this red color is that it is due to evolved organic material that results from the chemical processing of methane that once escaped from Pluto's atmosphere and were then captured by Charon and condensed on Charon's cold poles. Okay, let me now finish by discussing the atmosphere of Io. Jupiter's satellite Io, of course, is a unique world. It is the only extraterrestrial place with confirmed current active volcanism due to tidal dissipation by Jupiter. So this volcanic activity it has a variety of manifestations, including an active and quickly resurfaced surface, which is covered by SO2 frost and by other sulfur species, and has also a number of other volcanic manifestations like hotspots, plumes, lava lakes, outbursts. Both the plume and the sublimating frost lead to the production of a tenuous atmosphere, which partly escapes at a rate of about 1 ton per second, and which then forms a torus of neutral and ionized material around Jupiter, which in turn may interact with the atmosphere and the surface itself. Io's atmosphere has been discovered by Voyager more than 40 years ago, and since then there have been a number of observations of this atmosphere from the ground. And the number one goal of all these observations has been to try and answer the essential question of the nature and source of Io's atmosphere. Is this atmosphere primarily supported by sublimation equilibria or directly by active plumes? Ultimately, of course, Io's atmosphere is of volcanic origin, since the frosts are deposited by condensing material that falls from the plume. But I think that the question of the main immediate source of Io's atmosphere is not a vain question, because in fact, volcanic atmospheres and sublimation atmospheres can be fundamentally different in terms of their vertical structure, their dynamics, their lifetime, and their response to insolation changes. Io's atmosphere is now detected in several wavelength range, and each technique has in fact its own limitation, modeling issues, and ambiguities. And furthermore, a general limitation is the fact that, at least from the Earth, we cannot observe the night side of Io. But despite all these difficulties, the observations have reached a consensus on the fact that Io's atmosphere is permanently present and observable, temporally relatively stable, variable but in some, I would say, organized way, and also spatially variable but moderately. There is now also an agreement that the atmosphere is mostly concentrated at low to mid latitudes with maximum pressures of about 2 nanobar, and that there is more SO2 gas on the anti-Jovian hemisphere compared to the hemisphere that faces Jupiter. Well, this distribution still does not tell us what the primary source of the atmosphere is, because both the SO2 frost and the volcanic hotspots appear relatively widespread on Io, and also because they tend to be concentrated at low to mid latitudes. In fact, the best way to observationally discriminate between a sublimation and a volcanic atmosphere is to study if and how the atmosphere will track or not variation of the surface temperature, and therefore variation of the solar of the insolation. And in this respect, a very nice result was obtained from mid-infrared spectroscopy, which, although does not resolve the Io disk, can determine the disk average content, SO2 content of Io's atmosphere. And by repeating this measurement year after year over a full Io year, so 12 years, and taking advantage of the fact that Jupiter and Io heliocentric orbit are significantly eccentric, it was possible to show that the SO2 content of Io's atmosphere varies annually in a way that is inversely correlated to the distance to the sun. Therefore, it can be said that Io, like Pluto, has an annual pressure cycle. And the authors of this work showed that their data can be interpreted as the sum of two components, one variable, sublimation driven, and one that's independent of the distance to the sun, and therefore presumably volcanic. And the volcanic component accounts for about 30% of the atmosphere when it is at its maximum near perihelion. As I explained, Io's atmosphere is not robust enough to maintain uniformity in surface pressure, so people have tried to model how the surface pressure varies horizontally and as a function of local time. So in some sense, these are the equivalent of the general circulation models we have seen for Pluto. These models include all of the relevant physics for calculating surface temperatures, including the eclipse by Jupiter, and then all the atmospheric dynamics. And a complication for this model is that because the atmosphere becomes collisionally thin on the night side, then the fluid approximation does not hold, so particle models must be used. So here are some model calculation for the SO2 column density as a function of location on Io and on local time. And you see that there are very large variation between the day side and the night side, typically 3 orders of magnitude. And this model also predicts that during eclipse, the SO2 columns are expected to drop by 1 or 2 orders of magnitude. One other nice result of this model is that they naturally explain why more gas is observed on the anti-Jupiter hemisphere than on the sub-Jovian hemisphere. And this is a consequence of the eclipse, which affect only the sub-Jovian atmosphere and which cause the surface temperature and therefore the sublimation to be lower on the sub-Jovian hemisphere compared to the anti-Jovian hemisphere. What do the observations say about that? Well, of course, we cannot observe Io's night side from the Earth. So in recent years, people have tried to use eclipse by Jupiter as a proxy of the night side. And there is now a mounting consensus that, that there are variations of Io atmosphere in eclipse, but not at the magnitude predicted by the sublimation only model. So the first evidence that Io's SO2 atmosphere decreases in eclipse was obtained again from this mid-infrared data, where there was a clear decrease of the SO2 gas band depth after Io enters eclipse. And from that, it was estimated that about 80% of the atmosphere condenses during eclipse. So it's a significant fraction, but it's not a factor of 10 or 100 decrease as model predict. Most recently, new insight on this problem has been obtained from very nice ALMA observation of Io in the millimeter, observing Io when entering eclipse or getting out of eclipse. Of course, the great advantage for this is that these observations are disk resolved, which permits to image the evolution of the atmosphere as it goes in and out eclipse. So what you see here is the evolution of the SO2 line emission as Io proceeds into eclipse and how the emission is progressively restricted to the volcanic centers. And here you see the reverse phenomena here for Io going out of eclipse, where here in eclipse, the emission of SO2 is restricted to volcanic center, and then on a time scale of about 10 minutes or so, the sublimation atmosphere is being reinstalled. So this is very interesting, and it shows that Io has a sublimation component that varies during eclipse. And so all in all, and although there are still a number of open questions, the picture of the origin of Io's atmosphere has been considerably clarified in recent years. It is established now that there is a coexistence between the sublimation and the volcanic sources. And not only is this established qualitatively, but it's now quantified, and we can predict more or less or characterize what are the fraction of the two components as a function of location on Io and as a function of time. Io atmosphere, however, is not only SO2. And there have been models of plume chemistry, and these models, in fact, try to predict the composition of the plume as a function of the chemical composition of the erupting lava and as a function of the physical condition in the eruption. So in principle, measuring Io's atmospheric composition provides a window into the condition of in the erupting magma. So these are model predictions from these thermochemical equilibrium models. And remarkably, a few of the species that have been predicted have been detected in addition to SO2. These are like SO, S2, and salts, KCl and ACl. However, we are not yet quite able to exploit this because there are several complications. For example, some species like SO are not purely volcanic. They can also be produced from the secondary photolysis of SO2. And a further complication is that, rather surprisingly, the distribution of the gas that are thought to be volcanic in origin do not always appear collocated. So, from an observational point of view, the other major remaining unknowns regarding Io's atmosphere are the vertical temperature structure and the atmospheric dynamics, although in both cases, there are detailed model predictions, both from one-dimensional and three-dimensional models. So the sources of heat for Io's atmosphere are solar input, plasma heating, and Joule heating, and the heat sinks are radiation from SO2, both in vibrational bands and rotational bands. These models generally predict that Io's upper atmosphere must be very hot, up to maybe 1500 K, but in contrast that the lower atmosphere should remain cold, typically below 200 degrees in the first kilometer. This is true both in the one-dimensional models here or in three-dimensional models. But unfortunately, the observation sends us very conflicting messages in this respect. And the different techniques to observe Io's atmosphere return essentially any value from 100 to 600 K for the bulk temperature of Io's atmosphere. So we have not yet measured properly even the mean temperature of Io's atmosphere and even more the vertical temperature structure. The millimeter observations are potentially very rich in information because they do resolve spectrally the lines. But unfortunately, we still understand very well what is the physical mechanism that causes their shape. In fact, it's not really understood whether the lines are broadened by temperature effects or by velocity fields. And in fact, there are a very detailed prediction of what the dynamical regime of Io's atmosphere could be, but very little observation. So we have essentially three possible dynamical regime for Io's atmosphere. The sublimation models predict essentially a sublimation flow from the day side to the night side and from low latitudes to high latitudes with divergence of the flow at the hottest point on the day side and convergence at midnight. And they also predict that, as expected, based on the previous consideration on surface atmospheric equilibrium, there are strong supersonic winds across the terminator. The volcanic models predict plume-like dynamics with rising and falling motions, re-entry shocks, and so on, either with the surface or with the sublimation atmosphere, which produces very complex velocity fields. But there is yet a third possible dynamical regime, which would be caused by the interaction of the plasma flow with the atmosphere. This plasma flow may induce a drag force on the atmosphere and put it in motion in a circulation regime that, depending on where Io is on its orbit, could mimic, as seen by the observer, a day-to-night flow or a night-to-day flow. So we have three different possible regimes, very different, but observations are extremely limited. And in fact, no observation has really confirmed any of these regimes. So Io's dynamics remains a very uncertain topic and a very active topic of research. So in summary, I hope I have illustrated a bit a few physical aspects involved with the tenuous atmosphere of the solar system. As we saw, a lot of progress has been done recently in characterizing the atmospheres of Pluto and Io. Pluto in particular is a fascinating example, I find, of an atmosphere that shows resembles and differences both with Mars and Titan. It has resembled with Mars in terms of surface-atmosphere interactions, and it has resembles with Titan in terms of atmospheric chemistry. In some sense, it's a mini version of both Mars and Titan. So to wrap up, I am listing here a few open questions that remain to be solved. I am not going to read them, but I will leave them to you, and perhaps you'll have idea actually about solving them. Thank you very much for your attention.